Hello everyone. In the last class we have seen cyclic group and index. In this class we are going to see Lagrange's theorem. This is very important 10 mark question. In unit 5 this only is the biggest question. So listen carefully. The statement is, if G is a finite group and H is a subgroup of G, then order of H is a divisor of order of G. So we have to come with the proof. What is given? G is a finite group. The next one is H is a subgroup of G. G is finite means surely H is also a finite group. So will implies the subgroup H is also a finite group. The next we are seeing one theorem for last class. For that theorem we are using here by there is a one-to-one correspondence between any two right cosets of H in G. So using this theorem, here we have to say we have two right cosets having the same number of elements. So will implies using this theorem, which implies we have any two right cosets of H in G have the same number of elements. So we have to take two elements A and B. So HA and HB have the same number of elements, we have to say. That is, if A and B are elements of G, then the right cosets HA and HB have the same number of elements. Moreover, we can say H itself is a right cosets of H in G because H is equal to H, because E is a identity element. So we have to multiply it with the identity element. H is equal to H. So the number of elements in each right coset is order of H. So we can say order of HA is equal to order of HB is equal to order of H. HA and HB having the same number of elements, but the element was not same. Suppose in HA we having the elements 3 and 4 and HB we having the elements 5 and 6 means both HA and HB having the same number of elements but not same elements. So easily we can say order of HA is equal to 2, order of HB is also 2. We are using that only, we can say order of HA is equal to order of HB is equal to order of H. In the next step, we have to consider distinct right cosets of H. So for that number, we have to consider K. Let K be the number of distinct right cosets of H in G. We get that any two distinct right cosets we have no common elements. Already I told HA and HB having the same number of elements but not same element. The same concept here we have to use. We get that any two distinct right cosets we have no common elements, but each has order of H elements, since order of HA will be equal to order of HB. Since any element A belongs to G, we have G is equal to, so G have distinct right cosets of H in G. So distinct right cosets will be K. So we have to take G is equal to HA union, HB union, etc. up to K times. So we have to put order means that is also same. So order of G is equal to order of HA plus order of HB plus order of HC plus etc. That is also for K times. Already we are mentioned order of HA is equal to order of HB is equal to order of H. So here we have to use that step. So we have to write order of H plus order of H plus etc. That is also for K times. So we can write K into order of H. So in the next step will implies directly order of H is a divisor of order of G. So for this we have to see two corollaries. The two corollaries also very important. Suppose in the question we are asking the corollary statement means First, you have to write the Lagrange's theorem. Using this theorem only, we are proving this corollary. So, you have to write like this because surely it will be appear in the 10-mark question. So, corollary 1. If G is a finite group and A belongs to G, then order of A divides order of G. So, first we have to consider order of G is equal to n. That means order of a group is equal to 10. We have to take element from G. A belongs to G is an element of order m. That means the order of that element is m. So, listen carefully. Order of G, that order of group will be n. Order of an element that A belongs to G, that order of A is equal to m. So here listen, let order of G is equal to n. Let A belongs to G is an order of, let A belongs to G is an element of order m. M is the least positive integer. Therefore, order of an element definition we are writing A power m is equal to E, will implies order of A is equal to m. The next we have to consider A is equal to H is equal to the generator of A, that is cyclic group generated by A. So using that definition we are writing A power 0, A power 1 etc. up to infinity. Now H is a subgroup of G, so we can say order of H is equal to m. Since already we are told order of G is equal to n, order of A is equal to m. H is a subgroup. For that we are mentioning H is equal to a cyclic group generated by A. So easily we can say order of H is also m. So by using Lagrange's theorem, order of H divides order of G. So m divides order of G. Here the order of G value will be n. So m divides n. Suppose in a 10-mark question, your question is like this, means if G is a finite group and A belongs to G, then order of A divides order of G means you should write the Lagrange's theorem statement and proof. By using this theorem only we can say order of A is divides order of G. Up to this we are written means we get full mark. Otherwise you won't get full mark, that will be half of the mark. For this simple proof they won't give the half of the mark, only they have put 2 or 3 marks. So listen carefully, it will appear in the 10-mark question, means you should write the Lagrange's theorem and proof. Afterwards only we have to come with the corollary proof. The next corollary is, if G is a finite group and A belongs to G, then A power order of G is equal to E. So here we are using corollary 1. So by corollary 1, if G is a finite group and A belongs to G, then order of A divides order of G. So order of A divides order of G means we can write order of G is equal to m into order of A. Suppose order of A is equal to 2, order of G is equal to 8 means 2 divides 8. So we can write 8 is equal to 4 times of 2. That 4 will be we are considering m. So here we are using 8 is equal to 4 into 2. So order of G is equal to m into order of A. For this we have to go for A power. A power order of G is equal to A power m into order of A. In power we have multiplication, means we can write the whole power. So here A power order of A, the whole power m. A power order of A means that will be compulsory the identity element E. So E power m. Identity element will be 1. 1 power anything is 1. So order of A power order of G is equal to E. So the second corollary also we have to proved. So in the 10-mark question, the second corollary statement will be appeared, means you should write Lagrange's theorem and proof and corollary 1 statement and proof. Finally, we have to come with this corollary 2 proof. So listen carefully, this is very important. So tomorrow assessment is only you have to write Lagrange's theorem statement and proof, corollary 1 statement and proof, similarly corollary 2 and statement proof. So you have to study the statement also. Thank you.